Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we're going to start the circle chapter. Really important. As one of my students said, I always say this, but I say it because it's important. This is going to be heavy on the SAT and the ACT. Circles are really, really important. So please make sure that you understand everything we're talking about and ask questions. I'm going to go through the first couple of slides relatively quickly, because we've already learned this, so I don't want to bore you. A circle, of course, is a set of all points in a place that are a given distance from a point in a plane. And did I just say in a place? I'm sorry. A circle is a set of all points in a plane that are a given distance from a point in the plane. What I'm talking about here is the radius, okay? A circle is made up of this center point and then a bunch of all these other points that are equidistant to the center. They're all equidistant to the center. And when you put all of these exterior points together, and you connect them, they create a circle, okay? So, the center of the circle, we know what the center is. It's labeled there for us nice and neatly in this circle diagram that I gave you. And of course, that given distance, okay, from the center to any exterior point along the circle, any, is called the radius. And someone already mentioned it, ARAC, all radii are congruent. I went ahead and reminded you of that. So again, a circle is a set of points that are all equidistant from the center. And that distance is called the radius. Plural for radius is, of course, radii. All right? So nice and simple. Okay. Some definitions for you guys. First one, we're going to talk about concentric circles. Two or more coplanar circles with the same center are called concentric. Concentric. Wow, what's wrong with me in reading today? Concentric. Concentric. So it's two or more circles that are on the same plane, of course, and they share the same center. Literally. It's that simple. Okay. Number two. Two circles are considered congruent if they have congruent radii. So not only are radii within one circle congruent, but circles with congruent radii are considered to be congruent as well. So if you've got two circles and they have the same radii, guess what, gentlemen? They are congruent. Number three, a point inside, that means in the interior of a circle, okay, if its distance from the center is less than the radius, is called an interior point. Okay? So an interior point is a point that is inside the interior of a circle, and its distance from the center is less than the radius. So A here would be an interior point because it's inside the circle and it is less distance than the radii. The radii, or the radius in this case, goes from here to here. Point A from the center just goes here to here. So it is a shorter distance than the radius. Yes, sir?
Let's say in a proof, you would ask us to prove two circles congruent, and then by doing that, we'd obviously have to prove that the radii are congruent to two circles. What would we say is sufficient that those two circles are congruent?
Okay, the question was if we have to prove in a proof or in a question that two circles are congruent and we're trying to prove that the radii are congruent, it would probably be mathematical in that case. I would tell you the center and then the point along the circumference of the circle. You'd use the distance formula, and then you'd prove that those two distances are equal for both circles, then you would know that both radii are congruent, and then if two radii are congruent, circles are congruent, and that would be a definition. So you could even just say definition of congruent circles. All right, my man? Thank you so much. That was a great question, actually. Okay? Is everyone with me here so far? Okay. Number 4. This is an exterior point. An exterior point is a point that is outside in the exterior, okay, of a circle. And its exterior point, if its distance from the circle is greater than the radius. It makes sense. The radius goes from here to the circle's circumference, and then point C goes through the circle, beyond the circle's circumference, is outside of the circle, so therefore it is an exterior point. And the distance from the center to an exterior point is greater than the radii. For number 5, this is a point that is on a circle, and a point is on a circle if its distance from the center is equal to the radius. When you're looking at the circumference of a circle, guys, I want you to think of circumference like a perimeter of the circle. It's not called perimeter because perimeter are for polygons. I always remember that. Polygon starts with the letter P. Perimeter starts with the letter P. So perimeters are for polygons. Circumference starts with the letter C. That's for circle, which starts with the letter C. When you look at the circumference is made up of an infinite number of points that are equidistant to the center. We've already talked about this. So if a point is on the circle itself, and you connect the center to that particular point, you have just created a radius. Okay? Sounds pretty basic, but I need you guys to really understand how and why that works, the mechanics behind it. Okay? Not bad, right? So far, not bad. Just a lot of stuff to memorize, but most of us pretty much already knew this, okay? That's why we're going kind of quickly. I'm sorry about that. Okay, now, chords and diameters. Okay. Let me go ahead and put up the drawing here so everyone can see what chords and diameters are. Okay. So, points on a circle can be connected by segments called chords. Okay? There are two types of chords, really. A chord, just a chord straight up, is a chord of a circle is a segment joining any 2 points on the circle. Okay? As you can see here in green, this is a chord. I have this point on the circle, this point on the circle, and I connected those 2 points that were on the circle, and I created a chord. Awesome. Now the diameter. The diameter of a circle is a chord, because by definition it goes from one point on a circle to another point on a circle. So it is by definition a chord, but it passes through the center of the circle. So a diameter is a chord, but a chord is not a diameter. It's kind of like in polygons. A square is a parallelogram, but a parallelogram is not a square. Okay? So, again, the diameter is a chord because it is the connection or a segment that goes from one point on the circle to another point on the circle. However, it goes through the center of that circle. So again, a chord is not a diameter, but a diameter is a chord, and it goes through the center. Sir, thank you.
So a chord can be a diameter.
No, a chord cannot be a diameter. A diameter is a chord. A chord cannot be a diameter because by definition, A chord just goes from one endpoint to another. If that segment happens to go through the center, then it's a diameter.
No, what I'm saying is like, for example, sometimes
No, no, I know what you're saying, and I'm not trying to be rude. A chord is not a diameter. A diameter is a chord. Think about it like this, like I had told you, with parallelogram and square. A square is a parallelogram because it meets all the criteria of a parallelogram. But can I say a parallelogram is a square? No. Because no, you can't, because a parallelogram doesn't have four right angles. A parallelogram doesn't have all equal sides. So a chord is just a chord. Now, if that chord happens to go through the center, it's called the diameter. So the diameter is a chord, but a chord is not a diameter. Be careful with that. It's a great question. I hope I'm totally not trying to be sarcastic. It is a very big question. It's one of those that sometimes I'll tell you, if it was an always, sometimes never question, that's probably why you're thinking about it. If I said, is a chord a diameter? Never. Never. Is a diameter a chord? Always. Does that help?
yeah,
You promise, my man?
yeah.
Thank you. Great question, sir. May I continue, gentlemen? Thank you, gentlemen. Okay, circumference, very simple. Circumference, like I already explained to you, is the perimeter of a circle, and circumference equals 2 pi r, or diameter pi. We had already talked about this fact a while ago. I just didn't want to bore you. Please remember, though, that the radius is the diameter divided by 2, and vice versa, the diameter is 2 times the radius. So depending on what they give you, you can find the circumference with the radius and or the diameter. It really depends on what they give you. Now the area, okay? I don't know if we've really talked about area in detail here, but I need to explain area to you guys because most people don't really know what area is. Area explains how many square units are inside of a figure. Let me explain real quick. Let's say you have a house, okay? Not the most fancy house, but right there. There you have a house, okay? And they tell you that this house has 2,000 square feet. Guys, what that means is that you have 2,000 individual 1 foot by 1 foot squares throughout that house. That's what it means, guys. That's what square footage is. It's how many of these square units do I have inside of the figure. So if whatever, they tell you that a country is 235 square miles, that means that there are 235 squares that are 1 mile by 1 mile. Does that help put a definition to area? Because a lot of times people don't understand that correctly. Yes, sir. Never, never. What's up? Okay, thank you. Very good question. My boy was asking, does 3D count like the walls? Okay, that's called surface area. And we're going to get into surface area later. But when we're just talking about area of a figure, we're talking about how many square units inside of that particular figure. So for this house, if you notice, I didn't draw a 3D figure. When they tell you the square footage of a house or an apartment or whatever, a space of some sort, it's just of that plane figure on one single plane, two-dimensional. That's a great question, okay? So that being said, the area of a circle is pi r squared. So if I have a circle, guys, and I tell you it's 8 square feet, that means that there are 8 1 foot by 1 foot squares that can fit inside of that circle. Please understand that concept. If I tell you something has 46 square meters, that's the area, that means that there are 46 squares that are 1 meter by 1 meter. If I tell you it's 7,200 square inches, that means that there are 7,200 squares that are 1 inch by 1 inch. It's how many square units inside of a figure. That goes for polygons, circles alike. Does that make sense? All right. Radius-chord relationships. All right. The distance from the center of a circle to a chord is the measure of the perpendicular segment from the center to the chord. What did I just say? If I have this chord AB, okay, from the center, if I go ahead and drop down an altitude and stop at that chord, I create a perpendicular angle. Does that make sense? So OP is the distance from O to AB. Why? Because when I create a segment from the center to a chord, that is the distance from that center to that chord, and it creates a perpendicular segment. Yes, sir. We're going to talk all about what this implies now. I'm not trying to be rude. You'll see. But yes, to answer your question, you're awesome. Yes. Yes, sir. 100%. Okay? 100%. Does that make sense? You sure? Okay. Now, let's talk about some more radius-chord relationships. Now we're going to talk about theorems. The radius-chord bisector theorem. It states that if a radius is perpendicular to a chord, then it bisects the chord. All right? I'm going to prove why, guys. What this is saying is when you have a radius, okay, and I go through the radius, okay, and it is perpendicular to that chord, okay, if a radius is perpendicular to a chord, then it bisects the chord. So if I have this radius right here, and it is perpendicular to the chord, it is going to bisect that chord. And we have a very easy proof here. The given is that you have a circle O. The given is also that OD, which is the radius, is perpendicular to AB. So that's my given. No worries. Okay, give me 1 second, please. Okay, sorry about that. So that's my given. Number 2. AO is congruent to OB. Why? ARAC. All radii are congruent. Number 3. Triangle AOE, this guy right here, is congruent to triangle BOE right here. Why? Because of HL, hypotenuse leg, right? You have these two hypotenuses congruent, and you have OE, which is reflexive, and that's congruent. Yes, sir. Nah, don't worry about that. Yes, sir. Remember, I haven't proved that AE is congruent to EB yet. All I know is that AO is congruent to OB, and that OE is congruent to itself because of reflexive. I skipped a step. Yes? I skipped a step. That's what I just said. I skipped the reflexive step. You guys should know that by now. Okay? Thank you. Step 4, AE is congruent to EB. Why? Because of CPCTC. And then, of course, OD bisects AB. Why? Definition of segment bisector. So the reason I'm proving this to you guys is so you can understand what the heck is going on. But the fact of the matter here, if I have a radius that is perpendicular to the chord, all right, it goes ahead and bisects that chord. That's the bottom line here. Okay, now, I'm not going to rush faster than when I'm rushing. We may run out of time in today's class since we have a shortened schedule. If we do, this will be part 1, and we'll just continue part 2 tomorrow. It's not a big deal. Yes, sir.
There are many more ways to prove this, right?
What other way can you prove this?
Well, the theorem above, radius-chord bisector theorem, like it says that it also splits AE and EB congruent. So wouldn't that form a
That is this theorem right here, my man. The radius-chord bisector theorem. That's exactly what we proved.
yeah, exactly. So forming a perpendicular bisector theorem would also be congruent to OB, or you could just say that.
I just said AO was congruent to OB because of ARAC. Let's wait for the announcements. Okay. My class is having a little bit of a hard time understanding that I am simply proving this theorem, guys. That's all I'm doing. We know now for sure that if a radii or radius is perpendicular to a chord, it's going to bisect that chord. But why? This is the proof that proves the theorem. Another confusion that one of my students had, they said this, which is very valid. If I have these two congruent to themselves, if sides and angles, wouldn't this be congruent to this? Okay, and then these are two 90-degree angles, and you would have angle side instead of HL? Yes, but that's a more lengthy process. Okay, HL is a lot easier. So please, you can automatically use the radius-chord bisector theorem. For sure, guys. I'm just trying to explain to you why it is that it's there. So I'm going to prove all of the theorems that we're learning today. Okay? All right. Next, radius-chord perpendicular theorem. The radius-chord perpendicular theorem states the inverse is basically the converse of what we just learned. If a radius of a circle bisects a chord, then it is not a diameter. And it is not a diameter, then it is perpendicular to that chord. Okay? I mean, to that, then it is perpendicular to that chord. So basically here what's happening is this. Okay? I was given that you have circle O and OD bisects AB. Given. That's given right off the bat. I'm going to prove now that because OD bisects AB, I'm going to prove that it's perpendicular, that the radii is perpendicular to that chord. So number 2, we would say AE is congruent to EB, definition of segment bisector. Number 3, AO is congruent to OB, ARAC. All radii are congruent. Okay? Now, let's go back in time. Isn't O equidistant to A and B? Isn't E equidistant to A and B? So wouldn't that be the converse of the perpendicular bisector theorem? Or actually the perpendicular bisector theorem? If 2 points are congruent to the same endpoints of a segment, then it is the perpendicular bisector of that segment. So that is why this theorem is usable. Again, so now we know 2 things. If a radii is perpendicular to a chord, bam, it bisects that chord. We also know if a radii bisects a chord, bam, it is perpendicular. Okay, we can use those immediately. But again, I'm just trying to prove why we can use those. You with me here? Okay, last but not least, the radius-chord perpendicular bisector theorem. The perpendicular bisector of a chord passes through the center of the circle. Very simple here, very simple. What's happening here? Number one, you have OE is perpendicular bisector of AB. So right off the bat, you know that you have a right angle, and you know that it bisects the chord AB. So AE is congruent to AEB, definition of perpendicular bisector. OD is perpendicular to AB, definition of perpendicular bisector. AO is congruent to OB. All radii are congruent. And then again, we go now to the converse of the perpendicular bisector theorem, which states if 2 points, which in this case are O and E, are congruent or equidistant to the endpoints of the same segment, then it lies on the perpendicular bisector. So since this guy here, ED, is going upwards, that's why you have a little arrow there, but ED is the perpendicular bisector of segment AB, it's got to go through the center O. If a point is on the perpendicular bisector of the segment, then it is equidistant from the endpoints. So, although a lot of people don't like proving the theorems, that's what we did today. We proved the theorems. So what does the theorem basically state? States that if a radii bisects a chord, it's also perpendicular to it. If a radii is, or a radius is perpendicular to a chord, then it bisects that chord. And if you have a segment that is a perpendicular bisector to another segment, then that segment will be going through the center. This will be the end of part 1. Tomorrow we'll do the examples, and then we'll start homework together in class. Thank you very much. Have a wonderful day, and I hope you learned a lot, guys. Bye-bye. Bye, guys.